Dr. Corkindall, just so you know, you're muted.
There we go. Thank you for that. So in this first one, we're going to discover what X and Y being nilpotent mean today, but it means basically what it means for an element to be nilpotent is if you take a big power of it, it gets to be zero, right? And we'll see some examples of that today. But show that if X and Y are nilpotent, so if there's a big power of X that's zero and a big power of Y is zero, and there's a big power of X plus Y that's zero, and a big power of X times Y that's zero. Also show that if U is a unit, so that means it almost means it's one, and X is nilpotent, then the sum of U plus X is still a unit. And finally, show that if R is not commutative, then none of these necessarily hold. That is to say, if you have X and Y being nilpotent and U is a unit, X plus Y doesn't necessarily have to be nilpotent. It is X times Y, and it's also not true necessarily that U plus X is a unit. Now, you can hunt for counterexamples in number 3. My advice is to look at 2x2 matrices. Makes them easy, making them simple 2x2 matrices, and I think you can find counterexamples that you need here. Number 2, let R be a ring. We said the characteristic of R is some natural number n if when you take n times r, you get 0 for all r and r. What do I mean by n times r? I mean, remember, n is a natural number. I mean, r plus r plus r plus r n times. Right? So what this means is you can add r to itself n times. You get 0. That's like a finite order element in the group. Show that if r has an identity, then the characteristic of r is n if and only if n times the identity is 0 and n is minimal with respect to this property. And show that if you have an integral domain, and I'll explain what that is in a moment, then the characteristic of R is either a positive prime or 0. Number 3, we say, in number 3, we say that 1R, respectively 1L, is a right, respectively left identity of a ring. If when you hit anything on the right by 1R, it leaves it alone, or if you hit it on the left by the left identity, it leaves it alone. Give an example of a ring with a right identity, but no left identity. Right? Again, let me help you out here. Look at 2x2 matrices, and you might be able to find a ring in there that does the trick. Number 4 is commonly called the freshman's dream. You may have had friends in high school that did this. Anybody ever see somebody that go x plus y quantity squared is x squared plus y squared? And you know your teacher probably hit you over the head with a baseball bat for that, right? Because they forgot the 2xy in the middle, right? Well, it turns out that if you have a ring with characteristic p where p is prime, then that works. You have a plus b to the p to the n power, it's a to the p to the n plus p to the p to the n, which is why this is called freshman's dream. My hint to you is to do this by induction. It's actually fairly easy by induction. The base case being the hardest one. Number 5, you define a Boolean ring. And some of you that are interested in computer science, for example, may have heard of this before. But this comes up in computer science in particular. A Boolean ring is a ring such that x squared equals x for all x and r. Show that a Boolean ring is both commutative and a characteristic of 2. That always has to happen. And finally, the graduate problem is just kind of a fun one. I encourage you to try it. Suppose you have a ring with the property for every non-zero element in R, there is a unique, this is actually going to be important when we tackle this problem. The fact that B is unique, such that ABA equals A. Notice I'm not assuming that you can turn A and B around. ABA equals A, it has to be written this way. Show, number 1, And I would do it in this order too, because I put it in this order because it kind of builds on itself. Show that R has no non-zero zero divisors, and I'll explain what a zero divisor is in a moment. Show that if ABA equals A and BAB equals B, that's kind of cool. Build up to that, show that R has an identity, and finally, show that R is a division, which means that the reciprocal of everything is in there. I'll explain what a division ring is in a moment. So that is the homework for next time. There's a lot of definitions that you have to cover, and we'll get to most of them today. Let me recall for you what a ring is. It's just a non-empty set. Now with two binary operations. Under addition, this is just an old familiar friend. It's an abelian group. And it's got this other operation that we usually refer to as multiplication. And do two things nicely. Number one, I want it to be associative, right? I want it to behave that way. And I want it to play nicely with addition. So x times y plus z is xy plus xz. And y plus z times x is yx plus zx. Let me point out that if a ring is commutative, if the order of multiplication doesn't matter, then I only need one of these, right? This takes care of the case where the ring may not be commutative. Okay. So we looked at some examples last time. Let me give you yeah. You all have probably seen this in a specific context. In fact, you probably saw this in high school at some point or another. If R is commutative, so that is the order of multiplication doesn't matter, then we have the famous binomial. And here's what it says. If x, y is in our commutative ring, and n is an actual number, have y'all seen this? The way you take this thing and expand it, right? It's some crazy formula. K equals 0 to n of n choose k, x to the n minus k, y to k. Does that, it's ever involved? You guys have seen that at some point in the past? Where, in fact, this is a generalization of, for example, you've probably seen that, right? And more generally, what this is and this coefficient is determined in the middle. What all the coefficients are. This is n factorial, k factorial. Is that look a little bit familiar? Okay, and so you can take that as given. Using the binomial theorem at one point or another might be useful in the homework. Let me give you something that we're actually going to prove here. By the way, you can prove the binomial theorem by induction, because really the only thing that's going on here that requires as anything as relations between what these are often called binomial coefficients. Have you ever seen this in like a probability class or something else? But maybe actually, I think depending on the treatment of power series, sometimes they use that notation in Calc 2. Proposition 9.4. So here are some consequences. Let R be a ring. I'll go through the proof of at least some of this. Like this. 0 times A times 0 equals 0. You know, I should close the door, right? Because people walking by will look at that and say, yeah, I knew that the math people were all full of garbage, right? We got a bunch of people in advanced math class proving 0 times something is 0. However, there is something to this. Number 2, A minus A times B equals A minus B equals minus AB. All A, B, and I. And of course, when I say minus, I mean the additive inverse of A. So A plus negative A is 0. 3. Minus A times minus B is AB. If R has an identity, after we do some of these preliminary kind of things, I'll probably start writing the identity as 1 instead of 1 star. But and this, in fact, I just added this to the notes. And by the way, sometimes if I update the notes, I post that on my website because it's easier for me to do that. So if you ever want to check a more modern, I think I had been 5 like last night. M and N are actually in C, and R and S are in R. Then and let me add a caveat. So let me explain what this is. So what do I mean by multiplying an integer times an element array, right? Because remember, I'm a little worried this may be apples and oranges here, but it's not. It's just tomato, tomato. Because M is an integer and R is an element array. So let me tell you what this means. MR equals R plus R plus R n times. If M is positive and it is negative R plus negative R plus negative R, absolute value n times, if M is negative. So MR just means add R to itself n times if it's positive, and it just means add the inverse, the additive inverse of R to itself, the absolute value of n times if it's negative, and it's 0 if n equals 0. Okay. Let me prove a couple of these things, right? I mean, it would be kind of embarrassing if I couldn't prove that 0 times something is 0, otherwise I should kind of give wasn't on doing this stuff. So prove some of it. So let me point out that I don't know what this is. I mean, I hope it turns out to be 0, but let me point out that 0a minus 0a, whatever this is 0. Right? Because this is Cecil minus Cecil, so it cancels out. I don't care what this is, it's 0. And I'm going to use the distributive property here. And 0 minus 0 is 0. So notice I only did this from one side. The theorem also says that if I multiply 0 on the other side at 0, the proof is almost exactly the same. Okay, what about this next business? I'll prove again, I guess, part of this. If you look at minus AB plus AB, if you look at this right here, then this is minus A plus A times B. Right? Distributive property. But this is 0 times B. And we've just discovered that 0 times B is 0. So minus AB plus AB is 0. So this implies that minus AB equals the negative of AB. And if you look at number 2, we've proved that the first thing is equal to the last thing. Similarly, you can prove the second thing is equal to the last thing, and then everybody's equal. Okay, questions? So yeah, again, I did half of it, the other half being the same. The next one, let's see, look at minus A minus B. Well, by number 2, this is A times minus B, right? Because property number 2 says that I can switch out the minus sign from the first to the second. So really what I've done here is I've taken this minus and switched it over here, and minus B is B. Right, the inverse, the additive inverse of the additive inverse is the original thing. Oh, and I forgot to run a statement about this. Let me go back here and let me throw in something to number 3. So we should update number 3 a little bit. It says in the notes. I meant to say R has an identity. Yeah, that's the last thing. Then the identity is unique, and negative A is minus the identity times A. Okay, let's get back to the proof of that. Number 4. Suppose that I and J are both identities. That is, and what I mean by that is I and J, if you multiply anything in the ring on the left or right by either one of these, it leaves it alone. Right? So I can prove it's unique this way. When I multiply IJ by I, I, but now I'm multiplying J by I, so I get J, so I equals J. So it's unique, right? I mean, I almost feel like I got to take a shower after that one. I feel a little dirty, right? But it works because I is an identity, so I times J is J. J is an identity, so J times I is I. So I and J are the same thing. Okay. How about the other statement? So now, write identity one R, because we know there's only one of them now that we've shown it's unique. And look at this here, A plus minus 1, A is equal to right, because that A I can write as 1 times A. Now, again, I'm going to use the distributive property. Pulling that A out of the right there, and this is 0 times A equals 0. And so what we get is A plus minus 1R A 0. So I get minus 1R A. The last thing that I want to do is let's go through this claim here. And I'm only going to prove this with positive values of M and N. And I'll leave it as an exercise for you to figure it out from the negatives, but it's basically it's just replacing everything with its additive inverse. So it's very similar to the other ones. So 5 So we go by induction. So if what we have is 1 times R in S. Well, what this means, 1 times R just means add R to itself 1 time. So this is R times NS. And what do we mean for N? We mean adding S to itself N times. So this is R times S plus S plus S. However many times that do it, N times. Now, use the distributive property, and this is RS plus RS plus RS, still N times, which is exactly the definition of what this means. So here, this is 1 times N times RS, so it works for the base case. So for the inductive hypothesis, suppose N plus MN, or I'm sorry, MR in S equals NN RS. And now go up the ladder 1 for M. So consider consider this. Well, how are we going to do this? What is this really? This means add R to itself n plus 1 times. So this is right, because this is just a shorthand saying I'm going to add R to itself n times and then one more time, which is the same thing as adding it to itself n plus 1 times. Now, we have the distributive property. So this is MR NS. And this is R NS. And we actually already did this computation above. R times NS above. Well, and we also know that MRNS is MNRS. And we know also that this is NRS by the above. So what does this mean? This means I add RS to itself MN times and then another N times. So that's adding RS to itself MN plus N times, which is M plus 1 times N RS. Done by motion. Okay. Any questions? Okay, so I'm going to give you all some definitions that will be useful in what we want to do in the homework. So, definition. Not necessarily for anything, just a ring, and A and R. Number one, we say R, A, is a left zero divisor. If there exists B and R such that A, B, Z. If there exists non-zero. Yes. So what does it mean to be a left zero divisor? It means there's something that's not zero that you can hit on the left, and it makes it zero. So, for example, let me point out that if you have a ring that has something other than zero in it, zero is always a left zero divisor, right? Because if I let A be zero, when I multiply by B, it's going to be zero. Everybody agree with that? So zero always fits the definition. The question is, I mean, I don't know about you guys, but I'm used to it in my math. If I have, when this was the basic things when you were doing stuff in like high school algebra and stuff, probably two things being zero meant one of them had to be zero. But you probably experienced a situation in your math classes so far where that's not true. Anybody name me an example of where you might have two non-zero things and multiply and give them zero? Well, think about that for a moment, because I'm going to do some examples. Think about that. You say A is a right zero divisor. If there exists non-zero C and R such that CA equals. So if I can get something on the right by A and make it 0, something that's not 0, then it's called right 0. Finally, we say A is a 0 divisor if A is both the left and right. Now, here's a word of caution here. What it means to be a left 0 divisor is you can hit something on the left by it, it's not 0, and it turns into 0. What it means to be a right 0 divisor is if you hit maybe something else on the right, and it turns into 0. A 0 divisor means there's something that you can hit on the left and makes it 0, and something else you can hit on the right 0. That something doesn't have to be the same thing, right? So just because AB is 0 doesn't mean that BA is 0, but it still might be a right 0 divisor anyway. As long as there's something that works. 2. We say A is nilpotent if there exists n in the natural numbers such that A and n is 0. So, in a certain sense, this is even stronger than 0 divisor. What it means to be nilpotent is if you multiply A to itself enough times, eventually you're going to get 0. See if you can think of an example of that. 3. If R has an identity, then U in R is a unit. Yeah, I think. If there exists P in R such that U B equals PU 1. So what it means to be a unit is basically that it's invertible. Okay, any questions? And just so we can see our definitions a little bit, I'm going to try to work my way back across the board here. Let me give you an example. Okay, here's an example right here, Z6. This actually does have some 0 divisors in it. Let me give you an example. By the way, this let me clarify. You know how the addition works. This is like the clock. The multiplication works like the clock too. For example, what would somebody tell me when I multiply this? What would 2 bar times 4 bar be in this ring?
2 bar?
That is correct. 2 bar times 4 bar is 8, but then mod 6 is 2 bar, right? So 2 bar times 4 bar is 2 bar. So you multiply the same way you handle the clock. Of course, 0 is very silly, a 0 divisor, and of course, order doesn't matter with the multiplication screen, so everything's a 0 divisor if it's left or right.
2 bar times 3 bar is 6 bar, but 6 bar is 0. So those are your non-zero divisors.
Okay, that's right. So let me give you a stupid one before you give me the smart one. And the stupid one is 0 bar times 1 bar is 0, right? So 0 is a 0 divisor, no big shot. But he's right. 2 bar times 3 bar is 0 bar. So both 2 bar and 3 bar and 0 bar are the 0.
Would 0 be a 0 divisor? Because doesn't it have to be non-zero?
Yes, 0 bar times 1 bar is 0 bar. So I multiply 0 bar times a non-zero thing and I get 0. So it's a 0 divisor trivially. Right? Does that make sense?
Okay. Yes.
Why is 4 bar?
For the same reason, 4 bar times 3 bar is 12 bar, which is 0 as well. Also, in this one, notice if you look at the powers of 2 bar, this is 2 bar if n is odd, and 4 bar if n. And if you look at 3dn, this is 3 bar always. That's weird, right? You take the powers of 3 and you don't go anywhere, right? Because 3 times 3 is 9, which is 3, and so forth and so on. So this has no nilpotence other than 0. Because certainly every power of 0 is 0, so it's a nilpotent. Notice that 1 bar and 5 bar are units. Because 1 bar times 1 bar equals 1 bar, and 5 bar times 5 bar is 1 bar as well. Actually, it's easier to see that 5 bar is a unit when you think of it as 5 bar is another way to say -1 bar. So this example was chock full of all kinds of neat little things, but the one thing I'm a little disappointed in is the nilpotence, right? Only 0. Can anybody change this example? Change 6 to something else and give me an example of a nilpotent?
We could change it to 36.
Is that too much for me? Yes, 36 is what actually I like. I think I can handle that. So let me give you an exhaustive. I will break down every freaking thing in CMOD 36 and we'll see what we get. 36 is good, and the key. What made you think 36? Why does it work and my 6 didn't?
Because it's a square number, so I just squared the 6.
Right. So it's got at least a square there. That's right. So. Yeah, I'm not about everything else. So anybody want to guess what the 0 divisors are? I'm gonna have to write it. I'm gonna write it down.
It's the factors of 35, isn't it? Or 36.
Well, it goes away. You're right in spirit. It goes a little bit further than that. These are the 0 divisors. Can anybody pinpoint what this list of numbers has in common. What relationship do these numbers have?
Is it the GCD of those numbers and 36 is it doesn't equal 1?
That's exactly right. These are the numbers that share a non-trivial divisor with 36, right? So, and why does this make it a zero divisor? Well, let me point out that if you take, for example, let me pick a couple of them here, 33 bars. Why is that a zero divisor? What can I multiply? That's got one factor of 3 in it, right? It's 3 times 11. Everybody agree? So what do I need to make a multiple of 36? I need one more 3 and a pair of 2s. So how about 12 bars? And this should be 36. That should be 36 times 11 bars. So there, I multiply by a non-zero thing and it's 0. And notice that's what I'm doing. Like 21. Let's do 22 for example. I've got one factor of 2 in here. Well, let's pick up like another 2 and a pair of 3s. 36 times 11 bars. Actually, that's not right. I must have done something wrong here. Yeah, that's right. Which is 0 bars as well. These are the non-zero zero divisors. Anybody can guess what the middle focus are? And see if you can think along these lines. What has to happen to be a nilpotent? If I take a big power of it, it's eventually got to be divisible by 36, right? That's what it means to take a big power of this and make it be 0, is that it has to eventually pick up a multiple of 36. So, anybody want to guess what the nilpotents are? Ooh, let me get you started. See, this is a chance to get the easy one, right? 0.
6.
Okay, that's right.
We have 6. 12.
12, 24,
18.
18.
What do these have in common? They're multiples of 6, because to be a nilpotent, I've got to take a big power and get a multiple of 36. That means it's got to be divisible by 2, and it's got to be divisible by 3. And so if it's divisible by both 2 and 3, since they're relatively prime, it has to be divisible by 6. These are the nilpotents. Notice these are a subset of this. Notice these all show up as 0 divisors, but not all 0 divisors are nilpotent. No matter how many powers you take of 2, you're never going to get that 3 you need to kill it. Right? And it turns out, in this example, that everything left over, so let's go through the leftovers here. Let's see what we got here. Let's see what's left over out of this. 1, 5, 7, 11, 13, 14, 17, 19, 23, 25. 29, 31, 35. What are they?
Oh, sorry.
No, go ahead.
21 isn't what 25 is. What 25 is
Right, because 21 here has a factor of 3 with 36. But 25, that's only got 5s. It doesn't have anything in common with 36, right? Because 25 is 5 times 5. And 36 doesn't have any 5 times 5.
So it could be over there, even if it's not over there.
Well, in fact, they're exclusive. I mean, nothing here is here unless I copy something down.
Oh,
And nothing here is here. Right? And notice when you put these together, you get everything, right? Can anybody tell me what these, what's kind of the common sort of theme with these relative to 36?
They're relatively prime.
That is correct. These are the units. Every one of these has an inverse. Anybody know how to prove it? I think I've convinced you. Tell me if I'm wrong. I think I've convinced you that these are zero divisors and these are nilpotents. It's probably less convincing that these are units, right? How can you multiply 31 by something and get 1, right? Let me prove it. Suppose the greatest common divisor of an integer in 36 is 1. In fact, that's what it takes to be in this list. Everybody agree with that? These are just everything between 1 and 36 that are relatively prime to 36. What do you know about the greatest common divisor if I have the greatest common divisor, what's one of the first things we prove in this class? The greatest common divisor is a linear combination. So there exists A, B, and Z such that AK plus 36B equals 1. Do I agree with that? Now, in Z mod 36, 36B is equal to 0, right? So this gives us A bar times K bar equals 1 bar in Z 36. Because that thing's gone. And so this K bar is a unit. So all of these guys are unit. In fact, you might muck around with it and see if you can figure out the inverse of some of them. Let me give you another example really quick. Let me ask you all this question. I bet some of you can tell me. So this is a set of 2 by 2 matrices in R. You might have played around with this until you wanted to vomit when you were in linear algebra, right? So here's the question. Can anybody tell me what the units of this are? But what does it mean to be invertible, right? What does it mean to be a unit here? What kind of matrices can you multiply this by and you get 1 for the identity matrix? The units are just all the matrices that have a non-zero determinant. Because what happens to that? You can multiply it by its inverse and you get the identity matrix, right? Anybody want to guess what the zero divisors are?
The ones that have the determinant.
Right. Determinant 0. These are what you might have called in linear algebra the singular matrices. You can multiply it with something else and give you the 0 matrix. There's a lot of nilpotents. There's a more sophisticated. It's nilpotent if and only if all its eigenvalues are 0. But I don't know if you've seen that or not. The nilpotent, for example, look at that matrix. If you square it, you get 0. Let me point out one last thing. In these examples, I don't want to paint the picture to you that everything is either a unit or a zero divisor in a ring. In fact, that's wildly not true. In Z, 0 is zero divisor. The nilpotent. And the units are plus or minus 1. But everything else is neither a unit nor is it a zero divisor. 2 is not a zero divisor, and 2 is not a unit because 1/2 is not a unit. Okay, any questions? Okay, before we head out of here, let me announce again that today in the math club, the speaker is actually a former PhD student of mine who actually discovered something that has to do with the Big Bang Theory. And he proved something that was on TV, and there was actually some interesting media coverage of this. He and a rather famous number theorist from Dartmouth wrote a paper, and he's going to talk to us today. So it should be kind of an interesting sort of afternoon for you. I encourage you to be there. And other than that, I hope you all have a good weekend. If you haven't turned in your homework, don't forget to give it to me by 11. And have a good weekend.